So in our last class, we have discussed about the RL circuit, series RL circuit. In today's class, we'll go through series RC and then RLC together in series and a bits of parallel RLRC circuit. Okay, so we should start from here. Okay, so here you see here instead of inductor, we have taken capacitor. So what happens when we try to draw phasor diagram, that you have to check, because when we draw the phasor diagram and we take I as a reference phasor, I told, if you remember, that when we take series RL or RC circuit, then we take I as a reference phasor because same current will be flowing through each element. So if I take I as a reference phasor, then what will be the mm, uh, angle between voltage and current, voltage drop across capacitor VC and current. We know that the capacitive current will be leading by 90 degree uh, across VC. Okay, so if that happens, then how, if we can draw it, if I we take reference, then it should be 90 degree lagging, right? As I is leading VC by 90 degrees, so we can always draw it as VC, which is lag I by 90 degree, and of course VR will be in phase with your uh, current through the circuit. So once you have this, then you can always write this V, which is your input, that is equal to your V equal to I into R plus I into J into I into XC. So what is XC? XC is equal to 1 by omega C, where omega is the frequency of the source. So this is Vm sine omega t, and C is your capacitance. So if you have that, if you uh, have this relation, right, then you can write your I as V by R plus J XC. So you can write it as Z, where Z equal to root over of R square XC square angle tan inverse XC by R. Okay. So let us check in the next slide. That is what is done. So VR we can write as IR. This is I into XC. So this is square root of R square X square. And this is your impedance. So which is I into Z. So your Z is equal to root over R square X square. Okay. And XC is equal to this, that already we have seen in our previous class, that whenever it's a purely capacitive, then XC becomes like this, and your tan phi, this angle, I mean the power factor, will be equal to cos phi, which is equal to R by root of Z. So R by root over R square XC square. Okay, and tan phi is equal to XC divided by R. Okay, so if you want to draw it now, if this is your reference phasor, so if this is your reference, if we take V as our reference phasor, then of course your I series current through the circuit will be lagging, leading by a factor of 5, which is the power factor of this circuit. So earlier how we have drawn, this was your current through the circuit, series current. So this is your I into R, which is equal to VR, and then from here this is your VC, which is I into XC. So if you join these two, then you get your voltage V, which is applied to the circuit. So now if you take V as your reference, if we take V as your reference, this is the angle phi with which your current will be lagging or leading. In this case, for the
Leading.
capacitor, leading.
Leading.
So here we can see that zero crossing, if we check here, this is the zero crossing for V and this is the zero crossing for uh, phi. So it is not actually drawn properly. This one should be the phi. This is not phi. Okay,
And
so
sir,
this is
here it is written minus omega t minus phi. It should be plus, I think. I.
this one. Mm, huh, this is a typographical error. Anyway, so this is how we get our phasors, and then there is this is the case when we have R and C. But when you deal with practical capacitor, I don't know whether it was demonstrated in your series RLC circuit experiment. There in that capacitor, did you find the capacitor purely capacitive? Was there any loss across the capacitor when it was purely capacitor? Anything was discussed? Uh,
No, sir. Series RLC was discussed, not individual.
Okay, so what happens now in practical capacitor, there will be a dielectric loss, and because of that, what is theoretically happening, like if this is your VC, then I will be leading by exactly 90 degree. That scenario doesn't occur. So then what happens? It will be phi, which is less than 90 degree, and that happens because of the dielectric loss. So in case of ideal capacitor, it is one in which there are no losses and whose current leads voltage exactly by 90 degree, as shown by this figure. But practically every capacitor has some dielectric loss, and hence it absorbs some power, okay, from the circuit. Ideally when it is a purely capacitive, so one cycle it will be drawing, another cycle it will be sending back, as we have discussed. But in practically, because of the dielectric loss, there will be some consumption of power, and that due to this we'll get the phase angle which is somewhere less than 90 degree, just like this case. So we can approximate, we can just have a resultant of this, I mean resolve it into two components. So one component which this I will be like this is the perpendicular, and this is the in phase component, this is a quadrature component. So this particular quadrature component we can take as a resistive current, which is responsible for the loss, dielectric loss, and that we can model with the help of a fictitious resistance. Okay, so here what we have drawn, we are drawing this as
Hmm.
this is your I.
Hmm.
Please mute yourself.
Subrata Pal, please mute yourself.
Okay, fine, thank you. So here this is your phi now, which is less than 90 in the dielectric loss case, and this is we can denote as psi. So psi is equal to 90 minus phi, where phi is the angle between the voltage and the uh, capacitive current. Okay, so sine phi can be written as sine psi. This is psi. So sine psi is equal to sine 90 minus phi, which is equal to cos phi, where cos phi is the power factor for this capacitor. So in case of ideal capacitor, what will be the power factor? It will be zero. But when in case of practical capacitor, where you have some dielectric loss, you will get a power factor for the capacitor, which is cos phi. So since psi is generally very small, because of that resistive component or loss is not too much, so it will be close to 90, but not exactly 90, and this psi angle will be very less, say 5 to 10 degree, if let us assume that. So if it is very small, then sine of psi can be approximately written as psi, when psi we represent in radian. Okay, so then we can write it as tan psi is equal to psi is equal to cos phi. So this is actually instead of tan psi we call tan delta for the capacitor, and it is a very significant what rating rather we can characterize by tan delta or tan psi we have written here. So by this we can characterize the dielectric loss for a particular capacitor. So when we use the capacitor for a high voltage purpose, then it is very useful to carry out this tan delta test, so that we can find out the possible dielectric loss, what is the loss across this capacitor. So that is why it is an important parameter for the capacitor. So it is observed that the dielectric loss increases with frequency of the applied voltage, and hence phase difference increases with frequency f. So let us check later what happens, what is the relation with this dielectric loss with the frequency. So the dielectric loss appears as heat. So this heating effect can be approximated with the help of a I square R. So that is the fictitious resistance which I am talking about to model your dielectric loss. So we have written is as RAC. So it is imagined that the capacitor consists of a pure capacitor with an equivalent resistance, either is in series or in parallel. So usually we follow this parallel approach rather than series. But let's see what happens when we take the resistance, this RAC, in series or in shunt, which is RSH. So let us take the case when we assume the dielectric loss with a resistance which is in series with a pure capacitor or ideal capacitor. Okay, so in that case what will happen? It is a series circuit, so we'll take I as our reference phasor. IRAC will be the drop across this. So VRAC, and this is VC. So this is 1 by XC. So if you take the resultant of these two, this is your voltage. So what is your tan psi? This is psi actually. So what is your tan psi? Tan psi is equal to this divided by this. So this is actually your IRAC, and this is your IXC. And what is XC? XC is equal to 1 by omega C. So you can get tan psi, which is equal to RSC divided by 1 by omega C. So you get omega RAC into C. Okay. So we can write then that RAC is equal to tan psi by omega C. And earlier we have seen that tan psi, when the psi is very low, when psi is very small, tan psi will be approximately equal to cos phi. So we can write it as PF divided by RAC to be equal to PF divided by uh, omega C. So here for this case we can see that RAC, if omega is increasing, if we go for a high frequency supply voltage, then we get your RAC to be less, right? Because this is the if your PF remains the same. But what will happen when you increase your uh, omega C, your omega part, if you increase, your power factor will also change. Okay. So if we take the other thing, when we take when we have a parallel path, like you have a capacitor, and this is your RSH shunt, which is modeling your dielectric loss. Then this is your I current, this is I1, this is I2. So if we draw the phasor diagram, now we'll take I as our reference phasor. So I1, I2 will be, sorry, it is named in the other way. This should be I1. So I1 will be in phase with I, isn't it? This is your I, and this is your I2, and summation vector sum of this will give you your I. Oh, sorry. I should not write I here. I should, it should be corrected. Let me, just a second. Uh-huh. So here it is a parallel circuit. If we apply a voltage here V, which is your Vm sine omega t, Then we take V as our reference phasor because it is a parallel circuit. So this is your I1, this is your I2, or rather I2 will be leading because it is capacitive. So this is your total current I. This is your I2. So this is actually phi, the angle between voltage and the total current, and this is your psi. So psi is actually tan psi is actually I1 by I2. So you can write VRSH by VXC. So you will get this. So your RS shunt will be equal to 1 by omega c into tan phi. So earlier we got PF 1 by omega c. So here also it is 1 by omega c. So if PF remains the constant, if you increase your omega, your RSH will be less. So power loss in the shunt resistance, we should calculate this, which is equal to omega c V square into PF. And here the loss in the series resistance, because this is actually your dielectric loss, isn't it? So whatever we, if we model it by series or shunt, whatever it is, loss should be same. So we can see this is omega into CV into PF, and then this is equal to I square PF into omega C, Y divided by omega C. So where PF stands for the power factor of the capacitor. So how can you write down the expression of the PF for the capacitor? This is equal to R by root over R square plus omega square c square. So this is how you can get the expression for the dielectric loss in case of a capacitor. Okay, I'll
Sir,
discuss a
in
few
the
things.
question it will be given that whether we need to consider resistance in parallel or series for the loss.
It should be specified. If the question comes like this, it should be specified that you can take you can model the ideal realistic capacitor or practical capacitor with the resistance in shunt with the ideal capacitor like this. So this slide is actually not complete. In the next class, just remind me after your midterm. I'll discuss more about this because it is incomplete. I'll come back to this. And for the time being, we'll skip this part Q factor and let us come to the series RLC circuit. So as it was decided suddenly, that is why I have to skip many slides. Anyway, we'll complete after your midterm. So now let us take the case of series RLC circuit where you have R, we have your VL and VC. So what happens, as I told, that whenever we'll draw the phasor diagram for a series circuit, we'll take I as your reference phasor. So we have taken I as your reference phasor. Then what is the drop across R? It will be in phase with I. So this is your VR. Okay. Ideally, it will be, if you put value wise, you will see that this will be more. VR will be more than I. So I should be somewhere here. It is better. Let us draw it like that only. So this is your I and this is your VR. This is your I and this is your VR. Then what is VL? VL, in case of VL, current will be lagging, right? Lagging the voltage. So voltage will be leading the current by 90 degrees. So we'll draw it like this here. This is your VL. Okay. And in case of capacitance, current will be leading voltage. So voltage will be lagging by 90 degree. So if we have from here, if we just do a series sum of this, either we can put it here and we can have the net effect, or from here we can just write your VC part, which is negative. So here whatever is left is VL minus VC. So then if you join these two, then you get your total V, which is your supply voltage. Okay, and then this angle phi is the effective angle between your current and your supply voltage V. So if you can see that supply voltage is V and your current is lagging supply voltage by phi, so it is mostly inductive because your inductive effect is more. Okay, so cos phi equal to R divided by root over, or we can write it as VR, because this is your VR by V. Okay, and V is equal to your, this is I into R, VR equal to I into R, this is I into Z, where Z is equal to R square plus XL minus XC whole square. Okay, where XL is equal to your omega L and XC is equal to 1 by omega C. Okay, so this is how you get your, from, if you draw the phasor diagram like this, you will get one case. Another case will be what, if you have your I like this, you have your VR like this, you may have VL like this, and you may have VC like this from here. So this is your net V. This is plus VL, this is minus VC. So this much is actually VL minus VC. So now see, it is downwards because capacitive voltage, capacitance is more, so circuit is capacitive in nature, and this is your resultant voltage which you supply, which is your supply voltage. This is your series current, and this angle is phi, where current is leading the supply voltage. So your circuit is capacitive in nature. And in some other case, we'll see that we have, if we have your XL is equal to XC, then this will come here. So you get your net voltage V is equal to VR. Okay, so we can write it like this expression now change. Earlier it was reactance for inductance, reactance for capacitance. Now it is the net reactance, which is XL minus XC. So which one is bigger we should take, and then accordingly we should take the square of that. And depending on the higher value of XC or XL, or power factor will be leading or lagging. So we can see it here. This is your effective impedance, and your, this is your power factor. And it is seen that the, if equation of the apply voltage V equal to Vm sin omega t, then equation of the resulting current in RLC circuit is given by this plus minus, because it will be plus when it is capacitive in nature, which is leading, when XC is XL, negative when XL is greater than XC. Okay, so it is almost the same thing. So how you can find your phi, that is shown that you can calculate from here, because once you can calculate cos phi, then cos inverse this will give you your phi, or you can find out using the phasor diagram, which is your phi equal to tan inverse XL minus XC divided by R. Okay, so we can write like this. If your, if we can write our V to be this, where it is a reference thing, we take this angle to be reference phasor, so this angle is 0, then we can write your uh, I equal to V angle this by Z angle phi. So then we can write it as V by Z mod of this angle minus phi. Okay, so if it is inductive in nature, so if it is capacitive in nature, then this will be V angle 0 divided by Z minus phi. So this minus phi is due to the capacitive nature. So you will get V by Z angle. So it is leading, and here it is lagging. Okay. So here is a table which is showing that if it is resistive, purely resistive circuit, value of impedance is R, angle phase angle for current is 0, power factor is 1. If it is impedance only, then 90-degree lag, power factor 0. If it is capacitive only, 90-degree lead, again power factor is 0. Resistance and inductance, it's like this. Lag from 0 to 90, power factor will be 0 to pf, 0 to 1, pf will be there. In case of capacitive also same thing, only lag will change to lead. And this is what happens practically, because whenever you have a inductor, there will be some resistance which you cannot ignore. So r, we can write it as small r plus j into xl. So this is the practical case. And capacitor also, as I told, that there is a tan delta angle with which we can characterize the dielectric loss. Okay. So that also can be modeled as a resistance. Either you can put it in series or in parallel. Usually we keep in parallel, and in case of inductor we keep this in series. Okay. And when it is a RLC circuit, then we take the difference between XL and XC, and that will be anything between 90-degree lead to so your theta or phi will be between plus 90 to minus 90. Equality also may hold. And between your power factor will be between 0 to unity, lag or lead. Okay. So let us now take one example. We'll try to show different example. So today is your last class, na? Before your midterm.
Yes, sir.
Yes, sir.
Okay. So I'll do something. I'll solve a few problem and I'll upload in your classroom so that you can refer it. Okay. Some solution of problems. I'll scan it and send it to you. So here what is showing, a current 5 ampere flows through a non-inductive resistance. Therefore, is non-inductive resistance we can do just winding in one direction and then in the other direction. In that way, we can make a non-inductive resistance with a choking coil supplied at a 250 volt 50 hertz supply. If the voltage across resistance is 125 and across coil is this, calculate the impedance, reactance and resistance of the coil. So it is having resistance, it is specified. It is not an ideal choke coil. Okay. And the power absorbed by the coil, the total power, and draw the vector diagram. So let us draw the circuit first. This is your resistance. This is the small resistance presence in the inductor. This is your inductor and this is your circuit. So this is capital R, this is smaller, this is L. So you have a series circuit. V is equal to Vm sine omega t, which is equal to 250 volt RMS value. V is equal to 250 volt 50 hertz. So what is given? It is given that current equal to 5 ampere. What else is provided? Drop across resistance is 125. So this is your VR. So VR by I will give you your R, isn't it? Which is equal to, okay. So as I told that whenever it is a series circuit, then we should have a current as our reference phasor. So if we get our I, then this is our VR, not drawn to scale. VR is 125, I is equal to 5 ampere. Now I have to redraw it because there is not enough space here. So this is your I, this is your VR. we got what is your resistance. Then what else is given? It is given that the voltage across resistance is to 125 and across coil is 200 volts. So coil is having some resistance, so which will have a drop across. We don't know how much it is. So this is I into R, and then I into XL. So this is the voltage drop across the coil. So this is V. We should write RL kind of. So VRL is given, which is equal to 200 volt. So VRL by I will give you, this is your actually small r square plus XL square. Okay, agree? We don't know what is small r. We know what is, we don't know what is L. Only thing is we know omega equal to 314. So we can write it as 314 into L whole square. This is one equation. What else is given? This, if you know that sum of these two is equal to your total voltage, isn't it? This is your total voltage, which is equal to 250, right? So you can calculate the angle phi from here. So what is this? What is this angle? It is, uh, we can write it as, otherwise we can create one more equation, which is equal to I into 25 plus small r. We know I equal to 5. So that is this total resistive drop, right? And another is 5 into XL. So that whole square plus 5 into XL square is equal to 250 square. Or in the other way, you can write like this. You know what is your total impedance. Z is equal to R plus small r whole square plus XL square. So from there also you will able to find out. So I into Z is equal to 250. So you can write that Z is equal to 50, and that is equal to 25 plus small r whole square plus XL square. So here you are finding this, which is r square plus XL square is equal to 40, and 25 plus r square plus XL square equal to 50. So if you solve these two, you'll be able to find the value of what? R, isn't it? What will be the result? So it will be 50 square minus 40 square is equal to uh, uh, 25 plus r. So it's a 25 square minus r square. That means it is 25 plus 2r into 25, isn't it? And XL will cancel out, and this side will get 90 and 10. So from here we can find out what is the value of r then, isn't it? Because this will be 36 this side once you calculate it. So your 2r will be equal to what it is. If you subtract 25, it will be 11, so 5.5. Okay, so we got r equal to 5.5. So once you know r equal to 5.5, if you substitute here, you'll be able to find out your XL. And if you know XL, from there, if you divide by 314, you will get the yeah, impedance, reactance, everything, and the value of the inductance, that also you will get. And the power absorbed by the coil is what? It will be V into V, 250 into I, 5 into cos 5. What is cos phi? It is for this particular circuit, your Z equal to this, and what is your R. Small r capital R so you can get cos phi from there. Okay. So that is your cos phi. So there, I think the same approach is done, but in a different way. Let us also go through that. I have done in a different way. Here it is done in a different way. Let's see how it is done. So it is for this particular thing, it is BC square plus CD square equal to 200 square. Yes, we have done this. Then what is CD? That we can find out from here, because mm, we know what is BC, because BC is equal to 125 plus this. This is one equation. BC square plus the same thing they have done. BC square plus CD square equal to 200 square. This is one equation, and 125 plus BC into CD square equal to this. So same thing they have done. They got what is equal to BC, and that if it is divided by 5, then we'll get R. So in the same way it is done. Just instead of writing this IR and all those things, they have named it and then solved it. Okay.
Sir, minus BC square, that part I could not understand. That part can you explain?
Actually, what this is equation 1 and this is equation 2. So we did this only 2 minus 1.
Oh, okay.
Just like here we did now. Uh, I have not shown this equation 1, this is equation 2. So I found r square plus xl square equal to 40 square, and 25 plus r square xl square equal to 50 square. So I have subtracted from second equation first equation, then xl will cancel out. So we are left with 25 plus r square minus r square equal to 50 square minus 40 square. Then I use the formula of a plus b minus b. Okay, got it? So for this particular problem, first you have to draw the phasor diagram, otherwise it will be difficult for you to understand. Okay. So tell me whether it is clear to you, otherwise I'll repeat.
Yes, sir, it's clear.
Okay, so let us go to a next problem. So here what is given, two coils A and B are connected in series across a 240 volt 50 hertz supply. The resistance of A is 5 ohm, the inductance of B is given, but resistance given for the A, but inductance is not given. For coil B, inductance is given, but resistance is not given. So that we have to calculate. And if the input from the supply is 3 kilowatt and 2 var, that means here you are given the I square R loss and I square XL, your active power and the reactive power. So let us see how we can solve this. We can draw this like this is your, just a minute. This is your RA. This is your XA. I write in terms of XLA or XA. And this is your RB and XB. So you are connected with 240 volt 50 hertz supply. And uh, it is given that your your active power is equal to this 3 kilowatt, and reactive power equal to 2 kvar. Oh. So we know that active power square plus reactive power square is equal to instantaneous power or volt ampere. So that if we solve, we can write it like 3 square plus 2 square. So this is your instantaneous power. You know, or volt ampere. You know what is the supply voltage, that is equal to 240. So what is the current through it? It is 240 divided by root over 3 square plus 2 square. So that will be the series current flowing through it. So if you can calculate this, the expression of the current.
Sir, is it the unit is kilo volt ampere for the total power?
KVA, because it is in kilowatt and kilowatt. Okay, so accordingly we should put the sign. So it is kilowatt. That means we should take that 10 power 3, and accordingly we should solve it. How much is your current through it? So that we can find out from here. If we know the current, then we can find out the I square. We can write it as I square into RA plus RB equal to 3, and I square into XA plus XB equal to 2, isn't it? So because I square R is your active power consumption, which is 3 into 10 power 3, and you know what is the value of I. So from here you can find out your RA plus RB. So from here you calculate what is your RA plus RB. Out of that, RA is given, resistance for A is 5 ohm. So your RB will be that minus 5, right? So you will get RB. And for the other case, it is given, you know what is I, so you can find out what is XA plus XB. So that you can get from here, because I is known. So now what else is given? RB, LB is given. So you can write as XA is equal to this plus, both are inductive in nature, so no need to subtract and all. So we can write it as 314 50 hertz supply. So omega equal to 2 pi f. So 2 into 50 is 100, and that pi is 3.14. So 314 into point is equal to, you know what is that. So you can find out this expression minus this 314 into 0.15 divided by 314. So that will give you, this is your XL. So your LA will be that divided by 314. So then you will able to find out the LA part and the RB part. So I think same thing must be done here. So this is your volt ampere. Then from there we can find out what is your current. If we know current, from there we can find out your RA plus RB. That is what is done. RB we have calculated. Now impedance is this. Okay, they have not used the relation I square, uh, I square into XA plus XP. So that is also correct, but they have done in a different way. So as your RA plus RB is already calculated, so that is known to us, which is equal to this 13.3, and we can calculate the overall impedance by dividing the input voltage 240 divided by this current. This is the current. So that if you do, you get your impedance Z. So XA plus XB is equal to impedance square minus resistance square, which is like this. Out of that, XB is this. So you can find out what is your XA, and subsequently what is your LA. Okay, so this approach is also correct, and that is also correct here what we have calculated. So you can verify it from here. I don't have calculator right now. Anyway, let's try how
Sir,
we can do
one
this.
question, sir. In your approach, sir, you did I square into XA plus XB equal
Hmm.
to 2000 or 2. So that one
It
will
should
be
be 2000, then
okay.
because
Okay.
kilowatt is there. So those things you should take care of. Huh? This is kilowatt. So 2000. Because what we know, I square into R.
Sir, but it current is not coming same, sir, by this one. It is coming like 0.0665 ampere.
0.06. Which one? Circuit current.
Yes, sir. If we
You,
are
you, did you multiply with this?
Yes, sir. Sir, the KVA I did in denominator into 10 to the power 3. The previous slide, sir. In 74th,
Hmm.
previous one, sir, where you did I square R. Yes, sir. Sir, here I is equals to you have written at 240 by this. So, sir, this root over thing is in kilo. So I converted it into 10 to the power 3. I multiplied. So it is
I
coming.
think the slides are not the same. I'm in a different slide. You are in 76 slide. Which slide? Slide number
Yes, sir. This one only. This one.
76. Okay. What
Yes.
you did?
Yes, sir. So, sir, you have written I is equals to 240 by this under root. So, sir, under root I multiplied with 10 to the power 3 because it is in kilovolt ampere. So, then if I am putting in calculator, so it is coming
No, no,
0.
no. It is wrong actually. It should be KVA. If we can convert it into VA, then this into 10 cube, right? And this is I will be this divided by 240. I have written it the other way around because voltage into current will give you the instantaneous power. So
Acha,
this is
acha, okay, sir, okay, sir.
instantaneous power, and that if you divide with 240, then you will get the solution, which is supposed to be your 15 point something. 15.03.
Oh, yes, sir. Now it came. Yes, sir. My mistake, sir.
No, it is my mistake actually. I wrote in a different way, in the wrong way. Okay.
Okay, sir.
Okay. Then just a few things regarding your mm, solving problem. Let us go to a different slide. Next is your resonance, which we'll discuss later. This is your resonance. So let us go through this part. When we have a parallel circuit, then we can take the help of admittance instead of impedance. So that is shown here. Say we have a, as I told that whenever we have a parallel RL and RC circuit, then we always supply a constant voltage across the parallel path. So we take V as your reference phasor, right? And then on top of V, we take this current I1 and I2, and then we take their phasor sum to get the total branch current I. So for that, this is the approach actually. First, you should that I have already shown when I was discussing with your tan delta. So here you can see there is a RL path and there is a RC path. So if we take V as your reference phasor, your RL path, if the current through RL path is I1, so this is your I1, and you get this angle phi 1 as how it will be. Phi 1 will be tan inverse omega L by R, right? And for the other path, which is I2, it will be leading because capacitive in nature, and this phi 2 will be tan inverse 1 by omega C divided by R. So once you get this, then if you want to add these two, say we can write it like I is equal to I1 angle phi 1, which is lagging, plus I2 angle phi 2, which is leading. So if you have to solve this, you can always change from polar to Cartesian. So in your calculator, you will see that there will be rake and pole function. So if you want to convert from pole to rake, then you can use the command rake this value, I1 value and the phi value. So if you use this, then you will get the real component, which is your I1 cos phi 1 minus j into I1 sine phi 1. So by calculator straight away you will get it if you use the command rake and pole when you want to convert it. So one, if you use the command here rake, which is equal to 5 comma angle 45 something, or minus 45, if you put that, then if you put equal to, then you will get the real component. And then if you press RCL into F, if it is a uh, usual standard uh, calculator, then you will get the imaginary component. So please go through this part of your calculator, otherwise it will be very difficult for you to solve it. Okay, so similarly this one also, if you do, it will come as I2 cos phi 2, which will get straight away from the calculator, plus j into I2 sine phi 2. So now you collect your real and imaginary part, and then if you take addition of these two, I1 cos phi 1 plus I2 cos phi 2, this will give you real part. And then if you take j part, then I1 sine phi 1 minus I2 sine phi 2, that will give you your imaginary part. Then again you use the command pole, and there you first enter the real part and then comma imaginary part. Then you will get the net angle, which is your I, and angle equal to either minus phi or plus phi, whatever it is, after your this calculation. Otherwise you have to take the full complex algebra, and then you should take the root over of this square plus this square, and then tan inverse of that angle. So those things you can bypass when you use the calculator. Okay, like the way it is shown, these things, these steps, you can bypass it. Okay, so as I have shown here, they have done these things. So this is how it is solved. So these things you can do in an easier way when the parallel circuit will come. And one more thing, we can also write admittance, which is 1 by impedance, and you can write it in terms of ampere by volts like this. And then the conductance for any circuit will be this, your y cos phi, which is 1 by z into r by z. Cos phi is your r by z, so r by r square plus x square. And that also you can calculate like this: 1 by z, if we have z equal to r plus jx, that we can write it like r square plus x square. If I multiply with its conjugate, then this is your conductance, and the other part, j into x by r square plus x square, this is your susceptance. Okay, so you can do it from the complex algebra, or you can straight away write like this. And if you have a parallel path, then directly you can get first there, uh, this, for this part you can write the uh, admittance, say this is your yb, and if this is your ya, then you can write I as equal to v into ya plus yb. So in terms of admittance, then it will be additive in nature. So you can straight away add the admittance, and then you get your answer. Okay. So capacitive susceptance is positive and inductive susceptance is negative. That you will be able to understand, because when there is a inductance, there will be minus j term, and when there is a capacitance, there will be plus j. So it is the other way around. Okay, so in the susceptance, those things will be there. So here it is shown what happens when you can use the admittance. So this is another approach. If you can find this is simpler for you, then you can go through this part. This will help you to solve your problems when the complicated circuit problem will come. But I hope for the midterm there should not be much complicated sum on AC series and parallel circuit. Very elementary thing will come. I hope so. Okay. So with this, we conclude today's class. I'll be uploading a few more problems which are interesting, so that you can refer before your exam. Okay.
Sir, problems from Thevenin theorem and Norton theorem are going to come, right?
DC network theorem is there, but this time you can expect with dependent sources. Last time in your, and there will be a general question, midterm question paper for all the section. Okay, and mostly what we have decided, there will be dependent source related network theorem,